Oh, hi there. I didn't see you come in. Welcome to the exciting world of environmental toxicology, or toxicology for short. So let's start with the grandfather, the great grandfather of modern toxicology, Paracelsus, who said, quote, "All substances are poisons. There is none which is not a poison. The right dose differentiates a poison and a remedy." So, what he's saying is really the fundamental spirit of toxicology, in that the dose makes the poison. If you've ever heard the expression, too much of a good thing can be bad, or all things in moderation, that's really referring to the essence of the science of toxicology, studying the effects of different chemicals in different quantities. Some effects are positive or good for you. Some effects are negative or bad for you. For example, even water, which is a prerequisite for life, in large enough doses can be fatal. In fact, there are several examples in the news recently of people drinking too much water and dying as a result. In this case, it was a contest put together by a local radio station that basically had people chugging water to win a video game console. And this woman drank so much water that it killed her. And this is true for other chemicals that we are used to in our lives. Caffeine, for example. Apparently, there's such a thing as too much coffee, which is bad news for me. But in order to get a lethal dose or a lethal effect, that requires 118 coffees. So that's about 175 shots of espresso, kind of in one sitting. Alcohol as well. We see stories every year of college hazing rituals resulting in alcohol poisoning deaths from basically drinking way too much alcohol in too short a period of time. So, common chemicals, or chemicals that we're interested in studying in environmental health, can have varied effects based on different doses. So we see that alcohol, carbon monoxide, and even over-the-counter medications like aspirin, various sleep aids, ibuprofen, at different doses have different effects. So there is a non-toxic or beneficial dose to alcohol, carbon monoxide, etc. But as you increase the dose, you reach a level of toxicity. And as you continue to increase the dose, you reach a lethal effect. And the amount of substance required for each of those depends on the chemical that you're looking at. So essentially the toxicology field is the science of poisons, which I think sounds pretty cool. But to put it in a slightly more scientific way, toxicology is the study of all the adverse effects resulting from the interaction of chemicals or physical agents within living organisms. And this is why toxicology is being discussed during our pollution module. With pollution, we are interested in understanding the health effects of exposure to different types of pollution, whether it's air or something in the water or light or sound or any of the others that we talked about. So toxicology is really the science of understanding and quantifying that relationship between exposure to something and the subsequent health effect. So the use of toxicology in public health covers two distinct areas. One, toxicology is involved with the identification of potential health hazards resulting from exposure to certain chemical or biological agents. We'll talk a little bit more about hazards in a moment. The second distinct area, toxicology, is the assessment and subsequent recommendation to abate or reduce any resulting health effects. So essentially, find the thing that could be bad for you, assess it, quantify it, and then come up with a recommendation for how to mitigate the health effect. So kind of a classic public health framework or epidemiological framework. Identify the risk factor, study it, and then do something about it. So toxicity, a key part of toxicology. One would argue that you can't spell toxicology without toxicity, or at least some of the letters. Toxicity is the result of adverse cellular, biochemical, or macromolecular changes in the body as a result of exposure to particular chemicals. Many chemicals that we are exposed to will distribute throughout the body and will affect specific types of organs. Other types of chemicals may damage any cell or living tissue that they come into contact with. So, in other words, some chemicals result in toxicity for specific organ systems, and other types of chemicals will basically be toxic for any living thing that it touches. And there's a lot of things that influence the extent to which chemicals are toxic. The toxicity of a substance depends usually on a number of different factors. We're going to go through some of these throughout the lecture, but the point here is that there is a lot that goes into understanding the relationship between chemicals and health effects that go beyond just the identification of a chemical. We need to understand the chemical makeup. We need to understand the dose and what amount of dose or what amount of chemical results in a particular effect. We need to understand how someone is exposed to a particular chemical. And the effect is going to be different depending on the type of living organism. So different species will have different metabolisms. I think a good example of this is chocolate. Human reaction to chocolate is different than a dog's reaction to chocolate. So same chemical, different metabolic systems resulting in different effects. The life stage of the person or animal, from young to old, gender, the ability of the chemical to be absorbed by the body or tissue, the particular metabolism of the organism, how the chemical is distributed within the body, how the chemical leaves the body or is excreted, the general health status of the organism or individual, the nutritional status of that organism, and the presence of other chemicals that may act as a kind of amplification mechanism, resulting in a more toxic effect than if either of the chemicals were on their own. So let's look at this in simple terms, because that was a lot. But put simply, this is what we're trying to understand. Let's take a chemical exposure resulting from pollution, air pollution, the nasty stuff that comes out of factory smokestacks. We're interested in understanding how a person or group of people become exposed to that chemical. And once exposed, what will happen? Will exposure to this chemical make me sick? That is the essence of toxicology. What are the chances that the chemical exposure leads to a negative health outcome? So a couple of key words that we're going to need moving forward. And this is a FYI for your notes slide, but the general framework of the science of toxicology, determining health risks from exposure to various chemicals, a few important keywords to note. When we say hazard, a hazard is the source of potential harm. The evaluation of hazards in toxicology focus on defining what types of harmful effects may occur and under what circumstances. Essentially, the thing that is bad for you. Exposure refers to the interaction between the hazard and the individual. So for a hazard to cause harm, an individual or group needs to be exposed in some way. And there are different ways that people can be exposed. All of these different types of exposures will result in potentially different outcomes. And that refers to the route of exposure. How does that chemical actually enter the body? If you are exposed to the chemical, are you exposed for a short period of time or acute? Or are you exposed over a long period of time or chronic? Obviously, the acute versus chronic exposure situation will affect the outcome in many chemicals that we're going to look at. The dose refers to the amount of chemical and the amount of time that a person is exposed to the chemical. And finally, the response is how the body of the living creature reacts to a particular chemical. So toxicologists determine the different ways that the body might respond and determine the doses necessary to cause these different effects. So responses can be therapeutic or good. Responses can be deleterious or bad, like sickness or death. And the toxicologist wants to understand what doses cause those different responses. So we mentioned routes of exposure, how a chemical enters the body. And we can think about this in three main ways. A chemical can be ingested or enter the body through oral exposure. The chemical can be inhaled, or the chemical could result in dermal contact, contact with the skin. Once the chemical has exposed itself to the individual or the organism, it can either cause kind of general harm to any living tissue or any living thing that it touches, But more often, different chemicals will have different effects on specific organs. So some chemicals are specifically targeting the cardiovascular system or blood system. There are chemicals that are respiratory, reproductive, neurotoxic, nephrotoxic, or kidneys, and so on. So understanding what organ system is affected and what dose is needed to affect that particular organ system is an important aspect of this field. So, putting some of these keywords together, we have the fundamental framework of toxicology. So let's start with the hazard, which is the potential of something to cause harm. So can the chemical cause harm? This is the thing that we're interested in researching. And ultimately, we want to understand the risk of the particular outcome. So in other words, what is the probability that harm will occur following exposure to the hazard? And we link these two things together through the concept of the dose-response relationship. And we're going to spend most of our time talking about this concept. So here's an example of that dose-response linkage. Start with a little experiment. Grab your earlobes with your fingers. Just lightly, just enough to barely feel. Notice the pain levels that you're experiencing. Hopefully not much. Now squeeze your earlobes a little harder. You start to notice something. Finally, squeeze your earlobes as hard as you can. That's going to cause a painful reaction. In essence, this is the response and the dose relationship. So depending on the dose or the pressure at which you are squeezing your earlobe will dictate the type of response. This is the dose-response relationship that toxicology is really interested in looking at. And we study this relationship with these types of figures. For example, with the pinching of the ear example, on the x-axis at the bottom, we have the amount of pressure being exerted from not much all the way up to squeezing your earlobe really hard. On the y-axis is the amount of pain that we feel from that pressure, from no pain all the way up to a lot of pain. And if we measured the different types of pain reactions as we increase pressure, we can plot that, which is the red line in this example. And we can follow the red line to tell us how much of a dose results in a particular type of response. In other words, this is how we assess the interaction between the hazard and the risk, or probability of a response. So this figure is representative of the kind of fundamental framework of toxicology science, quantifying the health effects of some chemical hazard. So I mentioned that the basic principle of toxicology is this, that the dose is what makes the poison. So again, some things can be poisonous in very, very small amounts. Some things it takes a a great deal of that substance to become poisonous. So water, for example, or coffee. The particular chemical effects that some hazard has are typically dose dependent. In other words, the effect that the person has from that chemical exposure is determined by how much a person is exposed to. For example, chemicals that have helpful or therapeutic uses are harmful at a higher dose. So an example I can think of would be Tylenol or other over-the-counter pain medication. At a certain dose, typically the dose you see on the label, it tells you to take 1 pill or 2 pills, that elicits a particular response. Hopefully a response that lies somewhere in the feeling better end of the spectrum. However, if you continue to take Tylenol and take more than you're prescribed or more than what is stated or recommended, you begin to enter into a response that is worse. The dose response studies that are used in toxicology help to calculate the safe levels of various contaminants that may be harmful. So this is really one of the key sciences within environmental health. And this figure that we've started working with is really one of the main tools of this field. It's called the dose response curve. This is what allows you to quantify and understand the relationship between the amount of chemical or dose and the changing effect that it has. In other words, the amount of response increases as the dose increases. For some chemicals, there is a range at which there will be no observable effect. So in this example, you see as you travel from left to right on the x-axis, and as you start increasing the dose, you're still not seeing any increased effect until you reach a certain point. And once you reach that particular dose, you start to see the effect increasing. At which point you ultimately get to a certain dose that you no longer are experiencing the beneficial effect of that chemical. So that that middle part kind of represents the sweet spot between increasing dose and increasing effect. So the dose response curves are built or calculated based on the percentage of a group, people or animals, that respond as the doses increase. Basically, we want to take sort of the average or median response, because any one person might react a little differently than someone else. Remember that slide that showed all the different things that could potentially affect the relationship here. Not all people respond exactly the same way at a particular given dose. So we take the kind of overall reaction that a population has and use that to kind of understand, the typical reaction that a particular dose will elicit. So for example, if a particular chemical results in a reaction, or let's say negative effect, in half of the group that we're studying, 50%. So 50% at this particular dose have achieved a reaction. So this is used throughout environmental health sciences. For example, we've recently learned about studying air pollution. And we measure or quantify air pollution in a few different ways, one of which is the amount of fine particulate matter in the atmosphere, PM 2.5. So the figure on the left shows different concentrations of PM 2.5 in this region, some higher, some lower. And the figures on the right are dose response curves that represent the relationship between the concentration of air pollution and, in this case, the increased or decreased risk of mortality. So with figure, in this case, figure 3b, the one on the far right, follow the x-axis from 0 to 5 to 10. And once you get to 15, if you trace that line, if you go straight up and then follow it to the y-axis, about 2% of the population will experience mortality from exposure to that amount of air pollution. Continue to go up the dose, 15, 20, 25, and you see that you continue the increased risk of mortality in the population. So there's various ways that we can use these dose-response relationships. Dose-response curves are used often to derive dose estimates of chemical substances. We want to understand at what concentration or what amount of that chemical will produce a particular response. And a really common metric that's used is called the LD50, which stands for the lethal dose of 50%. This is a common dose estimate for measuring acute toxicity. And it's a statistically derived maximum dose at which 50% of the group that you're studying, rats, mice, people, whatever, would be expected to die. So if you give a chemical, let's say to a group of lab rats, and at some point you notice that after a certain dose, half of your rat population has died. Make a note of what that dose is, because that is your LD50. It's the amount of chemical substance required to kill or that results in the death of half the population. Again, not every single individual organism will react or respond exactly the same way. Some lab rats will die after a relatively small dose. Some lab rats may take a much higher dose to die from. But in general, when you reach that 50% mark where about half the population has died, that gives you a good quantifiable estimate of the acute toxicity of that chemical. There are other dose estimates that are also used. The LD0, or lethal dose 0%, represents the dose at which no individuals are expected to die. So at that particular dose level, you would expect there to be zero mortality. The LD10, or lethal dose 10%, represents the dose at which 10% of the individuals in your group die. So thinking of the lab rat example, if you reach a particular dose or concentration of a chemical, and you notice that 1 out of every 10 of your rats are dying, that is your LD10. And the LC50 you'll see sometimes, and that refers to the lethal concentration at 50% of the population. So this refers to the calculated concentration of a particular chemical that would be fatal to half of the group. So for example, looking at the lethal dose of alcohol, the LD50 for alcohol in people is about 5 to 8 grams per kilogram of body weight. That's the dose at which, if you were to administer that to a group of people, that dose you would expect to see 50% mortality. So for a 150-pound person, approximately 30 drinks in a relatively short period of time would be a sufficient dose to kill half of the people exposed to that dose. In other words, if a room full of average-sized people drank 30 drinks in 2 hours, half of them would die. And you can see on the right the dose-response relationship between alcohol and the particular health response. At very, very small doses, you'll probably notice little to no effect. As you begin to increase the dose, as you add drinks, you start to notice changing responses. So from giddy to sleepy to very sleepy to unconscious, then labored breathing, and at a certain dose, death occurs. But we don't always want to just measure mortality or how much of a dose does it take to kill half a group of lab rats. Sometimes we want to know how much of a particular substance results in a beneficial effect. So the effective doses are used to indicate the effectiveness of a particular substance. In other words, we're looking at a beneficial effect from exposure to a particular chemical. And some of the common specific endpoints are ED0, which is the effective dose for this percentage of the population, 0%. ED50 represents half of the group will have an effective dose or response, and so on. On the other hand, if we wanted to understand the relationship between the dose of a chemical and the toxic response, we can use the toxic dose estimates. These are used to indicate doses that cause adverse toxic effects. And some of the usual toxic dose estimates that you'll see, TD0, TD50, and TD90, referring to the toxic response at 0%, 50%, or 90% of the population. And often these metrics are used together to understand the relationship better between the dose of a chemical and the expected response. In this example, we have two dose response curves, one looking at the effective dose, one looking at the toxic dose. A dose that is between 50 to 75% effective, if you look at the corresponding toxic curve, does not cause much toxicity. So follow that line from the y-axis where it says response, and let's look at 50%. So if we follow that line until we hit the effective dose curve and then look down at our dose, that's the ED50. So that is the amount of chemical that is required for half of our population to experience a therapeutic or effective response. And you see that at this dose, the toxic effects have not yet begun. Once you go past this dose, once you go past the ED50, you begin to notice a toxic effect. And as you increase the dose, as you continue to increase the dose, you can observe the different toxic dose estimates. So for example, if you look at a 90% effective dose, that may result in a small amount of toxicity. So follow that 90% response, follow the dashed line until you hit the green curve, and then look down. That is the dose at which 9 out of 10 people or lab rats have experienced an effective dose. And you see that there's a little overlap with the blue toxic dose curve, meaning that a dose that is effective for most people will be a little toxic to a small percentage of that group. So often in pharmacology or in public health, we're interested in studying these two curves to try to find the sweet spot or a trade-off at which we're maximizing the effective dose and minimizing the toxic dose. We want to find that range in between where we have enough of the chemical that we know is going to cause most people to experience an effective response, and at the same time, a small proportion of the population experiencing a toxic response. So this is often done, again, with pharmaceutical studies, trying to understand different chemical exposures. We can compare these curves, and we can compare multiple substances. So, for example, the toxicity of various substances can be compared using the slope or the shape of the curve for each toxicant. Looking at toxicant A, for some substances, a small increase in dose causes a large increase in response. So as you follow the x-axis, as you go from a small dose to a large dose, you can see that once you reach a TD10, you see the curve very steeply increase. So it doesn't take much of an increased dose to result in a significant change in response. For toxicant B, other substances, a much larger increase in dose is required to cause the same increase in response. So look at the TD50 for toxicant A and look at the TD50 for toxicant B. Two different doses resulting in the same response. So toxicant A has a smaller dose than toxicant B, but achieve the same response. So here's an example of how we would use this concept to understand different pain medications and the response that they have. So again, classic dose response curves. On the x-axis, we see the increasing dose or the amount of the medication. And in this case, the response we're interested in measuring is the percent or the amount of pain relief. So starting with a very small dose, you can see that as we increase we see very steep pain relief effects for the first three chemicals. And once we get to 100 milligrams of a particular chemical, for example, acetaminophen, we see a slightly less or more moderate pain relief response. So this shows that different doses of these different medications will cause different pain relief responses. So if you wanted to look at the 50% mark, where 50% of our group experiences pain relief, follow that line for this first medication. I can do better than that. For this first medication, half of the population has experienced pain relief. And if we go down, that is the dose that achieves that effect. For morphine, it takes a little bit more. That is the dose of morphine required to have the same therapeutic effect as the hydromorphone. Similarly, codeine takes a larger dose. So just under 100 milligrams are required to experience the same effect as morphine. And then if we continue on, we see that acetaminophen, the dose required is much larger, and the maximum pain relief compared to the other three is a lot less. So essentially, these numbers are how we quantify the relationship between these chemicals in terms of the amount of dose and their response in the human body, pain relief. Similarly, we can look at the different types of opiates. A classic dose response curve. Let's look around the 50% mark. So half of our population experiences a therapeutic effect. And you can see that fentanyl requires the smallest dose. And then you can do the same thing with the other chemicals. So it takes much less fentanyl to produce the same effect as these other medications at much larger doses. So another way of looking at this, the difference between the effective dose and the toxic dose, if you compare these lines, so the purple line is the effective dose curve, the red line is the toxic dose curve. The shaded area here, the space in between these curves, represent the doses at which the substance produces an effective dose response, while the toxic dose response remains below TD50. So, look at the TD50 for this chemical, 40 milligrams per kilogram of this chemical. And at this dose, the therapeutic effect is seen in 75% of the population. So if the population is given 40 milligrams of this chemical, it will be lethal or toxic to 50% of the group and potentially effective for 75%. In looking at the relationship between fatal and effective doses for different chemicals, in this case, different drug chemicals, we can see in this case, relationship with alcohol. So at the very top, we have marijuana, which has a much higher ratio. And then we go down the list and we can see how different these different medications are in terms of their fatal to effective dose ratio when compared to alcohol, which is around 10. We can use this to understand, for example, the current opiate crisis in the United States and elsewhere, where morphine, heroin, or other addictive opiates are sometimes laced or contaminated with fentanyl, another powerful opiate. And you can see that, let's say the response here is 50% fatality. Half of the group taking this dies. How much fentanyl does it take to kill half the group? Really small amount, 0.1 milligrams. How much morphine would it take to kill that same group? 10 milligrams. So the dose needed to have a lethal effect is much smaller with fentanyl. Toxicology plays a critical role in the clinical trial process. So clinical trials are what all new medications or vaccines need to go through in order to be approved and deemed safe for human use. And all medications, your flu shot, your Tylenol, whatever, have gone through these phases. It begins with the lab phase, or the preclinical phase. This is where the chemicals are studied at a fundamental biological level. So basically, under a microscope, does it seem like the chemicals produce some kind of response or desired response in the organism? If it looks like that chemical has the potential to cause the effect we're looking for, it goes on to phase 1 clinical trial. The phase 1 trials are looking at basically whether the chemical, the drug, is safe for human consumption. So the dose response curve would be used in phase 1 trials to understand the dose given to study participants and their overall reaction. So what's the effective dose, for example, of half the group in phase 1? That gives you a sense of the strength or concentration or dose needed to achieve the results. So if you've ever wondered, how do they know how much Tylenol we're supposed to take? You look at the side of your pill bottle, and it says take a certain amount. This is based on the dose response calculations that are carried out during these clinical trials. If the drug is deemed safe in the small group of people, it goes on to phase 2. Here we see a much larger group, hundreds, sometimes thousands of people, followed over weeks or sometimes months to look at, is it safe amongst a larger group of people? Again, the dose response curve can be used to quantify the reaction of this population at certain doses. If it looks good, then it goes on to phase 3, which now is looking for not only is it safe, but is it effective? Does it do what we want it to do in most people? So again, we can use, for example, the effective dose calculations to understand what dose is needed, what should we put on the side of the pill bottle and tell people to take that will result in the largest effective dose and the smallest toxic dose. What ratio are we looking for? Past a certain point, if we take too much of that medication, we no longer get the therapeutic effect or the beneficial effect, and we begin to see an increase in the toxic effects. So early on in this process, the initial dose concentrations are worked out in animal studies. So typically, an experimental medication will be given to a population of lab rats in different doses, and their reaction will be recorded. So the graph on the right shows us at what dose does it take for 50% of the lab rats to die. And this tells us that about 15 milligrams of this particular chemical will result in half the lab rat population dying. That's the LD50. So clinical trials make use of this dose-response curve relationship to calculate what's known as the therapeutic index. The therapeutic index is used by pharmaceutical companies, doctors, etc., to compare the effective dose to the toxic dose. So, how much of this chemical will produce a beneficial effect, and how much is needed to result in a toxic response. The therapeutic index is used to basically tell you how safe a drug is. The ratio of the dose that produces toxicity to the dose needed to produce the desired therapeutic response is the therapeutic index, which is calculated as the toxic dose divided by the therapeutic response. So typically you'll see the TD50 metric and ED50 metric used. So the dose required for 50% toxicity in the population divided by the amount or dose that results in 50% of the population experiencing an effective therapeutic response. So for example, if we have a new medication that we're testing and we see that the toxic dose for 50% of the group is 200 milligrams. So it takes 200 milligrams to be toxic to half of the group we're looking at. And it takes 20 milligrams to produce the desired therapeutic effect in at least half of the group. So this gives us a threshold for understanding how much of this medication is needed to be beneficial, and then at what point things start to become no longer beneficial but toxic. So the index here, 200 divided by 20 equals 10. This is information that your doctor uses, that pharmaceutical companies use to compare different types of drugs and to understand their risk-reward kind of relationship. So a doctor would consider a drug safer to use if it had a TI of 10 compared to if it had, for example, a TI of 3. And again, the dose-response curve relationship is how we understand this therapeutic index. Comparing the slopes between efficacy and toxicity. So how do we get that ED50? How do we get that TD50 from that equation? Just follow the curve. Here's 50% response. Let's follow it until we hit the effective curve. So at this dose, whatever that is effective or provides therapeutic benefit for half of the population. Let's continue to increase the dose until we reach a point at which this dose is toxic to half of our population. So this range, this space, represents our therapeutic index. And it gives us an understanding of the sweet spot. How much dose do we need to be beneficial to the most people? And what dose should be avoided because it becomes toxic to most of the population. Another metric used by clinicians, drug manufacturers, etc., is the margin of safety, or MOS, for all the cool kids. The MOS is calculated typically as the ratio of TD1, or the toxic dose, to 1% of the population, over the ED99, the dose that is 99% effective to the population. So this gives us a conservative estimate for how much of the medication we need to produce the most good for the most people while minimizing the adverse effects for as many people as possible. So, for example, if an MOS gives you a number of safety, that results in, at that dose, 99% of the population that you gave it to would find it effective or beneficial. And at that dose, only 1% of the population would have a toxic response. So those are the dose response curves that are fundamental for the science of toxicology. And in public health toxicology or environmental health toxicology, we use these concepts and we use these tools to conduct what are called human health risk assessments. And human health risk assessments represent an approach that is used by environmental health scientists to better understand the health effects that a particular agent can have on the population. And the health risk assessment is based on the interaction between the particular hazard that we're interested in and the exposure. This gives us a risk index that we can use to understand how a particular chemical or agent will react in a population. Or should I say how a population will react to a given chemical. So when conducting a human health risk assessment, let's say the Environmental Protection Agency wants to understand what impact a new insecticide chemical will have potentially on the population, they need to know the following information. First, identification of the hazard. What are the potential health effects of a particular chemical? So what health effects does the new insecticide we're looking at have? We also need to understand the dose-response relationship. So at what levels are these insecticides harmful to human health? We also need to assess exposure. So how much of the insecticide, for example, are people exposed to in the environment? Finally, risk characterization. What is the risk of this new insecticide? This considers information on both the exposure and the dose response, and it gives you an idea of the risk to human health posed by, in this case, some new insecticide to the population. So a handy-dandy figure to keep all this straight. When conducting a health risk assessment, these are the steps required. Again, identify the hazard. We need to gather and analyze all our relevant data to identify the chemical of concern. So what is the chemical we're interested in studying? We need to start with that. Exposure assessment means we want to understand how humans might come into contact with that hazard. We need to identify the potential exposure pathways. We need to estimate the amount of that chemical someone might be exposed to for a given pathway. We also need to understand toxicity. We need to determine quantifiably the relationship between the particular hazard and how toxic it is. This information together will allow us to characterize risk. Risk characterization involves understanding the adverse health effects. For example, cancer risk. It allows us to understand uncertainty. So how well do we know the relationship between this hazard and the possible health effect? This is what the EPA or other environmental health groups use to study the release of pollution or toxic chemicals into an area and what effect that has on the population. So the Human Health Risk Assessment framework is used by environmental health researchers to address questions like, what types of health problems may be caused by environmental stressors, such as chemicals and radiation? What is the chance that people will experience health problems when exposed to different levels of environmental stressors? Is there a level below which some chemicals don't pose a human health risk? What environmental stressors are people exposed to, and at what levels and for how long? Are some people more likely to be susceptible to environmental stressors because of factors such as age, genetics, pre-existing health conditions, ethnic practices, gender, and so forth? And finally, are some people more likely to be exposed to environmental stressors because of factors such as their occupation, where they work, where they play, what they like to eat, etc., etc.? All of these questions can be addressed using the health risk assessment approach, which again relies on the basic principles of toxicology that we started the lecture with. So here's a little example of the human health risk assessment in action. If the video doesn't play, I will post it to the course website.
Example of a human health risk assessment. Residents in the country town of Victoriaville have expressed concerns that dust from an old industrial site is being blown over their houses and the local school and is affecting their health. A decision is made to do a human health risk assessment. Experts start the process. This can be a lengthy process that will be tailored for each situation. Step 1. Identify the issue and any chemicals that might be of concern. First, experts explore the historic use of the site, where dust is known to contain the chemical contaminant. Step 2. Identify the hazards. The experts look at environmental patterns, like the wind direction and rainfall, to understand where contaminant dust might be blowing over the town. They find that sometimes dust from the site blows over properties in the town, which could be a risk to the townspeople. Step 3. Understand how much of the hazard can cause harm. Scientists and health experts check against national guidelines to find out how much contaminant can make people sick if they breathe it in, or eat food with contaminant dust on it, or drink water with high levels of contaminant every day over their lifetime. Step 4. Assess who is exposed to the hazard, how people are exposed, and how much they are exposed to. The experts might take samples from soil and rainwater tanks and swabs from inside buildings where the dust typically falls. They might measure levels of contaminants in the air over a long period of time. They might also take samples from unaffected areas further away from the site, so they can compare the results. They test the samples to find out the levels of contaminant in the air, soil, water and dust. Step 5. Estimate the risk. Knowing how much contaminant is risky for human health, how long people are exposed, and how they are being exposed, the experts determine that in this case, there are no immediate or long-term risks to people's health, but they are being exposed to more contaminant than other people. The experts produce a report with their findings and some recommendations to help reduce the community's exposure to contaminant dust. The report may be peer-reviewed to ensure the findings are independent and accurate. Based on the report, actions are taken to make sure the people of Victoriaville are safe and healthy. In this case, advice to the community includes preventing dust from coming inside houses and the school, making sure children wash their hands after playing outside and that they don't put dirt in their mouths, washing vegetables grown in household gardens and the kitchen garden at the school before preparing and eating them. The owner takes immediate action and makes plans to reduce the amount of dust coming from the old site. The community is kept informed and engaged throughout the process. If you want to know more about public health, visit health.vic.gov.au. If you have concerns about your health, talk to your doctor or another medical professional.
So that's it. I hope that at least half of you found that informative. If so, I can say that this video has an effective dose of 50. Happy toxicologying!